Hello all, have a nice time. Today our topic of discussion is Fermat Kraitchik algorithm. In the last class we discussed about RSA crypto system and we found that the security of the RSA crypto system lies in the fact that it is very difficult to factorize a composite number into its prime factors. Today we will discuss two available algorithms, Fermat algorithm and Fermat Kraitchik algorithm, to factorize a number into its prime factors. First we will discuss Fermat algorithm. Suppose capital N is a composite number which can be factorized as u into v. Then this n can be written as u plus v by 2 whole square minus u minus v by 2 whole square. You can solve this one and you may find that it is equal to u into v. That is, any composite number, that is if a number can be written as u into v, it can be written in the form x square minus y square. So any composite number can be written in the form n equal to x square minus y square. So Fermat's method uses the function s of x equal to x square minus n and search for x such that s of x is a square. If you could find x and y such that n equal to x square minus y square, this can be written as x minus y into x plus y. Then clearly this x minus y and x plus y are factors of capital N. So our aim is to find x and y satisfying this relation. For that, we will take this function y as a variable of x. So we have s of x equal to x square minus n. And we will find an x such that this s of x becomes a square. If s of x is a square, this can be written as n is equal to x square minus something square, that is n is equal to x square minus y square. Then you can factorize it as x plus y into x minus y. So that's the method used in Fermat's algorithm. So to keep this s of x as positive, it is enough to find or enough to search x which is greater than square root of n. Now let this notation denote the largest integer less than or equal to, it is square root of n. Then we will search through x equal to largest integer less than or equal to square root of n, less than or equal to square root of root n plus 1, etc. So let us have an example. Let capital N is equal to 2491, which is to be factorized. First we will find square root of n. It is actually 49 point something, and the integer, largest integer less than or equal to that number is 49. So we start our search with x equal to 49. So s of 49 is equal to minus 90. It is not a square. S of 50, next number, s of 50 equal to 9, which is equal to 3 square. So we could find an x such that s of x becomes a square. So in this equation we can write s of 50 equal to 50 square, that is x equal to 50 here, 50 square minus 2491, or 2491 can be written as 50 square minus 3 square. S of 50 is 3 square. So this can be factorized as 50 plus 3 into 50 minus 3. So we have 53 into 47. That is, the factors of 2491 are 53 and 47. So this is the method used in Fermat's algorithm to factorize a given number. So a drawback on Fermat's algorithm is that if the number capital N is very large, the algorithm works just as poorly as trial division. There is a beautiful variation of Fermat's method due to M. Kraitchik using congruences. So we'll go to the next method, Fermat Kraitchik algorithm. So this is a modification of Fermat's algorithm actually. Here we fix x and y such that n divides x minus y into x plus y, n doesn't divide x plus y, and n doesn't divide x minus y. So we'll search for x and y satisfying these three relations. If n divides x minus y into x plus y and n doesn't divide x plus y or x minus y separately, this means that this x plus y and x minus y separately have some common divisors with n other than 1. So we can get some factors of n in that way. Okay. So here n divides x plus y into x minus y means that x square congruent to y square mod n. So this product is x square minus y square. So n divides this product means that x square is congruent to y square mod n. And here n doesn't divide x plus y and n doesn't divide x minus y means that x is not congruent to plus or minus y mod n. So this means that GCD of n and x plus y is greater than 1 and GCD of n and x minus y is greater than 1. For example, if GCD of n and x minus y equal to 1, then this implies that n must divide this x plus y, because n divides this product and n and x minus y have no common divisors other than 1, then n must divide this x plus y. So it is not possible by our assumption here. So we can conclude that with these assumptions, GCD of n and x plus y is greater than 1 and GCD of n and x minus y also greater than 1. So this GCD becomes a factor of n. GCD means that greatest common divisor. So it becomes a divisor of n. Then we will get a factor of n in that way. The algorithm is, first we find x1, x2, etc. xn such that x1 square congruent to a1 mod n, x2 square congruent to a2 mod n, etc. xn square congruent to an mod n. We will find such congruences starting with x equal to square root of n. Then find a subset xi1, xi2, etc. xir of this set x1, x2, etc. xn such that xi1 square into xi2 square into etc. xi square congruent to ai1, ai2, etc. air, where this ai1, ai2, etc. air is a square. So in this n congruences, we are selecting r of them such that the product of the congruences is here, given here, xi square, xi1 square into xi2 square into etc. xi square congruent to the right hand side becomes ai1, ai2, etc. air. The condition is this right hand side becomes a square. Now we are going to select our x and y. X is chosen in such a way that x is equal to xi1 into xi2 into etc. xir, and y is equal to the right hand side ai1, ai2, etc. air of the congruence, the whole raised to 1 by 2. So from this congruence we can conclude that x square, that is xi1, xi2, etc. xir square is congruent to right hand side becomes y square mod n. So this was our aim. We have to find some x and y satisfying this relation. So you will set x as xi1, etc. etc. xir and y is equal to ai1, ai2, etc. air raised to 1 by 2. Then this relation holds. Then we have x square congruent to y square mod n. That means that n divides x square minus y square, which implies n divides x plus y into x minus y. And if we choose x and y such that n doesn't divide x plus y and n doesn't divide x minus y, we have to choose x and y in such a way. Okay. Then GCD of this x plus y n is greater than 1 and GCD of x minus y n greater than 1, which are factors of capital N. So this is a way in which we will factorize capital N. So let us have an example. Let capital N is equal to 2041, which is to be factorized. Okay. So first we will find square root of n. It's equal to 45.1 something. We will start with the table xi, ai and the prime factorization of ai. Okay. So we, since square root of n is 45.1, we will start with 46. Okay. So we'll find 46 square congruent to which number mod 2041. Okay. This is first we want to find. So we'll find 46 square and divide the number with by 2041 and find the remainder. We'll get the remainder as 75. Then we have to factorize this 75 as its prime factors. So this is 3 into 5 square, 25 into 3, that is 75. Okay. Next number is 47. Then the remainder when divided by 2041 is 168. Its prime factorization becomes 2 cube into 3 raised to 1 into 7 raised to 1. Okay. Then 48, 263. Prime factorization is 263 itself because it is a prime. We will proceed in the same way, and here I ended with xi equal to 50. Okay. So let's start with the procedure. Our aim is to find some ai such that from this list such that the square, the product becomes a square. So if I choose these two ai's, what happens? So this is 3 into 3, it becomes 3 square, there is no problem. Then say 2 cube here, so it actually the product is not a square. So I have to choose some more lines to make this as a square. Now let us continue the process again. So I am starting with the first row now. So you have 3 here And if I choose second row also, this problem was 3 is completed. 3 into 3 is a square. Then 5 square, no problem, already a square. Then you have 2 cube here. So to make it as a square, I have to take some other row. So suppose I am taking this row, okay. So 2 cube into 2 cube, that is 2 raised to 6. The problem is solved. Now you have a 3 into 3 is already completed here. There is a 3 square, no problem. Now I want one more 5 and one more 7, okay. So it is benefited if you choose this row. There is a 5 and 7 here, and this one already is square. So I choose this row. So what happens if we choose these two rows, these 4 rows? The product of AIs becomes 3 into 3 into 3 square is square. 5 square into 5 into 5 is square. 7 into 7. Then the product becomes a square. Okay. So we'll choose our requirement x and y in such a way that x is equal to product of the x's in the corresponding rows. That is 46 into 47 into 49 into 51. It becomes this number, which is congruent to 311 mod 2041. You divide this number by 2041 and find the remainder. Okay. So that is our x. And y we have chosen in such a way that we have to write the product of AIs and take the square root. Okay. So actually here product of AIs are 3 into 3 into 3 square, that is 3 raised to 4. Then 5 square into 5 into 5, that is 5 raised to 4 into 7 square. Actually there is a 2 raised to 2 cube into 2 cube is 2 raised to 6, then 2 raised to 4, you have 2 raised to 10. So this is actually product of AIs. So I have to take the square root. So I have to choose 2 raised to 5 into 3 square into 5 square into 7. The product is 50400, which is congruent to 1416 mod 2041. So these are our choice of x and y. Okay. Now you can write x square is congruent to y square mod 2041. That means that 2041 divides x plus y into x minus y. X plus y means 311 plus 1416 into x minus y. We will choose the greater one as the x. So it is 1416 minus 311. That is 2041 divides 1727 into 1105. So this number divides this product. Now we will find the GCD of 1727 and 2041, or the GCD of 1105 and 2041. Then we will find one factor of 2041. You know the method of finding the GCD of two numbers using Euclidean algorithm. So you have 2041 is equal to 1 times 1721 plus 314. Then this 1727 is equal to 5 times 314 plus 157. And 314 is equal to 2 times 157 plus 0. So you know the GCD is the last non-zero remainder, that is 157. So you can conclude here GCD of 2041 and 1727 is equal to 157. That means that this 157 is a factor of 2041. So you can divide 2041 by 157 and you can see that it is 157 into 13. Okay. So we have factorized 2041 as 157 into 13. These two are prime numbers. And if you find the GCD of 2041 and 1101, you will get it as 13. Okay. And then you divide 2041, you will get 157. So it is enough to find the GCD of 2041 with any of these numbers to find one factor of 2041. Then you can find the other factor. So this is a method of factorizing a number using Fermat Kraitchik algorithm. Now let us discuss a question from your model question paper provided from KTU. The question was decrypt the ciphertext, this one, that was encrypted using the RSA algorithm using the public key NE equal to 2623,869. So let me remind you about the RSA algorithm. Here capital N is equal to 2623. That is a product of primes. Then E is equal to 869. So actually the process was we have to find the decoding key D. How will you find D? So actually this E was created in such a way that we have to find first phi of n and E is a number relatively prime to this phi of n. And you have to form a relation in such a way that lambda into phi of n plus mu into this E equal to 1, because we have chosen this E as relatively prime to n. So the GCD of these two numbers equal to 1. So you can find the numbers lambda and mu satisfying this relation. Okay, and we have already proved that this lambda becomes negative. And this particular mu, which is a coefficient of E, we will choose as D. So first of all, we have to find phi of n to write this relation. And to find phi of n, you have to find the factors of n, prime factors of n. If the prime factors are p and q, I can write phi of n as p minus 1 into q minus 1. So the first procedure is you have to factorize this n. So we'll start with square root of 2623. It's equal to 51 point something. Okay, so we start with 52, xi equal to 52, and we will find ai, and we'll find 52 square, and we divide by 2623. The remainder is 81. So when we write ai as the product of prime factors, it becomes 3 raised to 4. Actually, it is not necessary to write the coming rows because it itself is a square here. Okay, so we'll choose xi as x as, we will choose x as 52 itself, and we choose y as square root of 3 raised to 4, that is 3 square. So it's equal to 9. So these two numbers are when divided by 2623, reminders are these numbers itself. So this is congruent to 52 mod 2623, and 9 is congruent to 9 itself mod 2623. So that means that 2623 divides x plus y into x minus y, that is 52 plus 9, that is 61, into 52 minus 9, that is 43. So these are the prime factors of 2623 using Fermat Kraitchik algorithm. Then with this fact in your hand, you can find phi of n now. Phi of n is equal to p minus 1 into q minus 1, that is 60 into 42, and you will get 2520. Now phi of n equal to 2520, so you have to find this lambda and mu such that lambda into 2520 plus mu into this E 869 is equal to 1. We'll use again Euclidean algorithm to find the numbers lambda and mu. So by Euclidean algorithm, you will get lambda and mu satisfying this relation. Lambda into 2520 plus mu into 869 is equal to 1. And the coefficient of this E is mu. It is taken as our decoding key D. So we'll take this as a D. So our decoding code is D is equal to 29. Now let us go to the question. It is given that n is equal to 2623 and encoding key is equal to 869, and the text given is a ciphertext. So it is actually encoded, and we have to decode it. How will you decode it? Here you can see that the numbers are here 1030, 1511, 0744. All are numbers less than 2623. So we'll take each of the four numbers, each of the sets of four numbers, and we'll decode separately. So when you take 1030, how will you decode it? You have to take 1030 raised to D. D is we have chosen D as 29. So we have to find this 1030 raised to 29 and find the number divided by 2623 and find the remainder. That will be the decryption of 1030. So in that way, you have to decode this sets 1, 2, 3, 4, 5 sets separately and find the decoded number.